The first thing we're going to do is find x by setting 1 and 2 equal to each other. And we're going to solve out. So we're just going to throw in our algebra skills, put them to work. So 3x minus 10 equals 8. Now I'm going to add the 10. So this is just our solving through. Divide by 3 and x is 6. So now we can plug those into each of these. 3 times 6 plus 8, 6 times 6 minus 10. 6 times 6 is 36, minus 10 is 26. So angle 1 should also be 26, but we always want to try it. And so we get 3 times 6, which is 18, and 18 plus 8 is also 26. So that's angle 1 and 2. That's not 3, but what we know is that angle 1 plus angle 3 equals 180. Straight line right here. Straight line right there. So we could also have done the same thing with angle 2 because it's the exact same number. Subtract 26 and we get what one? 70, 60, 54. So 154 degrees. So the measure of angle 3 equals 154. If you don't know what those 3 triangles are, I don't know if Miss Griffin uses them. It just means therefore. You do not have to use those. Okay. So a measure of angle 3 is 154. Number 13, exterior angle theorem. So the exterior angle theorem means that the exterior angle of a triangle is equal to the sum of the opposite two interiors, or they're also called the remote angles. So we're going to add those up. So 5x minus 3 plus 4x minus 2. Together, they equal the exterior angle, which is 10x minus 20. So we're going to combine like terms, which is 9x minus 5. So once we have that set up, that's the geometry. Algebra kicks in from there. We're going to subtract. I'm going to subtract the 9x because I like to always move my smaller x value. So negative 5 equals x minus 20. Then we're going to add the 20. So negative 5 plus 20 is actually only 15. So there's x. We want to be cautious about what we're looking for. So CAD is this one over here. So we're going to plug in the 15 minus 20. 10 times 15 is 150, minus 20 is 130. So therefore, measure of angle CAD equals 130 degrees. Hexagonal prism, so that means the base is a hexagon. So a hexagon, 1, 2, 3, 4, 5, 6 sides. It's not a very pretty one. Its other base will also have 6 sides. And then they'll be connected. The corresponding ones will all be connected because I'm not connecting the proper ones here. This one goes over here. This one goes to there. And this one goes to the outside. You get the idea. Actually, this one goes here. I'm not connecting that one right. So there's a hexagonal prism in a very, very rough form. So if you're slicing and you're going parallel to the base, you should have the shape of the base. In fact, it should not only be a hexagon, it should be congruent to the base. If you go perpendicular to the base, because it's a prism, it's made up of those rectangles, so that will be a rectangle. And what's the largest possible cross-section? So this one is if we were to slice them diagonally, okay? So you're not going to go parallel or perpendicular, but you're going to have some kind of diagonal slice to it. And we talked about this. There's a video for you to see, and you can slice it any shape, any solid, to the maximum number of sides that it has. Okay? So they always have, in a prism, has 2 bases. Now the lateral faces, those rectangles, they connect the sides of your base. So how many are there? Well, because they're connecting the sides of the base, it's however many sides the base has. So the bases are hexagon. So this one has 6 lateral faces. So it has a total of 8. So what's the largest possible cross section? It can be an 8. You can say 8-sided figure, or it's an octagon. So some kind of octagonal shape if you were to slice, because it can slice. Your maximum slice can go through every single one of the faces, the lateral faces and the base faces. Okay, so if you didn't get the first one, I actually told you to fill this in when I just went through and gave hints that this is parallel. We're very sorry we didn't catch that when we were trying to make these on Monday for you. So we're going to write a formal proof. Now, my class doesn't use statement and reasons, and Miss Griffin's, I believe, does. So I'm actually going to do this twice. Do not bother to watch them both. Just watch the one that would work best for you. And I actually have some students who learned this before you transferred to Phoenix, and more than likely you also use the statement and reason proof. So just go to the next one and look at that instead of this way. I don't want anybody to be confused, and there's no right or wrong. You can do either one. Okay? So this would be if I'm not using the formal statement reason. So the very first thing you're going to do, and you're going to find if you watch them both, they're pretty much identical. We always start with the given. So we have to plot down our given. And we just do a comma in my class and say, where did that come from? It came from our given. So we know that BD is parallel to AE. Now we're trying to prove that they are similar. So similar means either we need to get two angles that are congruent, or we need two sides that are proportional with the included angle is congruent, or all three sides are proportional. Now, when we talked about these, we're like 99.9% of the time, you're going to be able to do angles. And when we have something like parallel lines, actually, this question back here, whether you needed to go over it or not, is the reason we can use angle, because every angle is either congruent to something else, and three other things actually, and it's supplementary to everything else. So we know lots of things about angles. So that's what I always like to start with. So we need to take this information from the given, look at our picture, and come up with either a pair of congruent sides or congruent angles or proportional sides. In our case, we can actually do angles. So if I know that this line is parallel to this one, sorry about the movement there, just hit the thing holding my phone. So I know these lines are parallel, and I'm going to extend them a little bit because that's where we end up with our 8 sets of angles. Okay, so we have our parallel lines, and then if we extended the transversals, which in this case are our sides, we end up with lots of angles. Now we're really particularly interested in the ones that are inside, the triangles. So we have this angle right here. Okay, angle CAE, or angle A, because there's no other angle there. That angle, if we moved it up here to the top one, would actually be this exact angle right here. So in our lines, it would be 1, 2, 3, 4 that are congruent. So those two are actually congruent. So we can actually say angle CAE, or we can just say angle A because there's nothing else there. It's congruent to this angle here. I can't use B because there's a B being used on both sides. So that one I have to use CBD. So we just do comma and we say, why do we know that? Well, what kind of angles are they? Parallel lines form corresponding angles. So we put a check mark. There's one there that we have, and we need to keep going. We're actually not done with the parallel lines yet because we can actually do this exact same thing on the other side. So this angle here, E, and this angle CDB are also congruent for the same exact reasons. So angle E is congruent to angle CDB, and it's the same reason. So parallel lines form corresponding angles. Now you might be thinking, oh, I have a different one, because we're actually done at this point. You only need 2 pairs of congruent to do similar. So I'm going to go down, and you can actually go to this one here that says triangle CBD is similar to triangle CAE, and the reason is angle. However, I'm going to put in here like a 3A. Actually, I'm just going to put an or for 2 or 3. Let's do that. Because we actually can do the third angle in this triangle. So the third angle in the top triangle is this angle up here, C. And if you notice, the third angle in the bigger triangle is also C. So another way we could do this is say angle C is congruent to angle C. And we have a reason for that. and that is reflexive. Anything that is congruent to itself in one triangle to the other triangle is reflexive property. So I'm writing 2 or 3 because you do not need all 3 of these for similar. You only need 2 angles. So you could have done 2 in this one, or you could have done 3 in this one, or you could have done the 2, 2, and 3. It's totally up to you. Okay, so like I said, I'm going to do this again, but I'm going to use the actual statement reasons to do this. Oh, I thought that that was my other review. It is not. So, no, it's not here. Okay. So I have it here. Don't worry. Okay, I'm going to pause it for a second. Okay, so we're going to do this with statements and reasons. So we call it a 2-column proof. That was a really bad line. I'm sorry. Okay, so the first thing we're going to do is we always start with the givens. So we have to label them down here. So BD is parallel to AE, and that is a given. Okay. Number 2, we're going to use that. We're going to say, all right, in looking at the picture, if I know that BD, and I'm going to extend these lines. So BD is parallel to AE. And the reason I'm doing that is most of the time when you see parallel lines, they're like this, right? And so it forms 8 angles. 1, 2, 3, 4, 5, 6, 7, 8. And 4 of those angles are congruent. The other 4 are congruent. And then you have supplementary for 1 from each section. What that means is these sides here, if we continue them, are going to be the transversals. So within that, we have 4 angles in the triangles. We have these 2 down here, A and E in the big triangle. And we have the 2 at B and D. So CBD and CDB as well. Okay. Are parts of the triangles, and they're part of these parallel lines. Well, if we look at this one right here, what would it correspond with? In the larger triangle, it would correspond with this angle right here. They're actually congruent. Why? Well, look at the parallel lines. If we were to push those 2 parallel lines together, A would move right up here to where CBD is. So that means that angle A, you can also say CAE, but you don't have to because A is the only angle at A, is congruent to angle. Now we have to use CBD because there's 2 B's there, right? So CBD. And we always need to give a reason for that. Well, the reason comes from up here. We use parallel lines. So parallel lines form congruent corresponding angles. For Miss Griffin's class, you may have had slightly different how she wants to do definitions. For my students from a different school, same thing. But as long as you get the idea that they're congruent and corresponding, most reasons will work. My class, we always like to put a check mark that says, hey, we've got one of our methods. We have 1 pair of congruent angles. Now, for the same reason, if we look over here, E and CDB are also congruent. So we can say that as well. So angle E is congruent to angle CDB. And it's the same exact reason. So you can do a couple of things. You can either write it out exactly. You could say same as 2, saves you a few there, and you can do the copy downs as well. Now we have 2, and we want to prove the triangles are similar. So we talked about those on another page. So if you're not sure about those, you should have actually gone back and done, I think it was like number 6 first. Make sure you understand the methods. So we have angle, angle, side, and side, side, side. We have nothing to do with side, so it's not side, 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 or side, angle, side. You only need 2 pairs of congruent angles, which we have. I'm going to leave a little space here because I'm going to go back to that in a minute. So number 4 is actually triangle CBD. This is our proof. Is similar to triangle CAE, and the reason is angle, angle. Now, the reason I left some space is because you might be thinking, well, I did it slightly different. So I'm going to write in here 2 or 3 could have been this. You only need 2 of the 3 pairs of triangles congruent, or angles congruent. But if you look at the big triangle, ACE, we have 1, 2, and its third angle is C. If you look at the top triangle, CBD, we have B, the one from B, the one from D, and we have angle C. So that means from one of our triangles is angle C, and the other triangle is also angle C. So we can say that angle C is congruent to angle C, and we learned that anything congruent to itself is because of reflexive property. You can also just write reflexive. So I'm saying that it's 2 or 3 because you only need 2 of the 3. Now, if you did all 3 and said that that was 4 and this was 5, that's absolutely fine. You can have 2 in this one, you can have 3 in this one, or you can have 2 and 3. As long as you have 2 of those 3, you're good. Next page. Okay, number 16, which I'm having trouble opening up to for some reason. All right, we're back to some formulas. If you read through my hints, we talked this through or watched my hints on this. You have to find the cylinder, which is the whole thing. You have to find the cone, which is like been sliced out, and that will give you the volume around it. So the volume of a cylinder, so we're back to our formula sheet. Cylinder volume is pi r squared h. A cone is 1/3 pi r squared h. So those are the two we're going to use. So the cylinder volume equals pi r squared h, and a cone is volume equals 1/3 pi r squared h. So a cone is actually 1/3 of the cylinder. So it's kind of nice here. We need a radius and a height. We need a radius and a height. The radius, they share a base, so they have the same circular base, so the same radius, which is 5. The height of the cylinder is 12, and you can see that the height, it goes right to the middle of the top base, the circle there. So it has the same height as well, which is 12. So volume equals pi 5 squared times 12. Volume equals 1/3 pi 5 squared times 12. We want an exact answer, so that means everything is going into my calculator except pi. So volume. So I'm going to put in 5 squared, which you can just do 5 times 5, which you already know that one anyways probably, times 12. So I get 300 pi. Notice I've got 5 squared times 12 here, right? The only other thing I have is 1/3, so I'm just going to take that number and multiply it by 1/3, or 1 divided by 3, and I get 100. So this one's 100 pi. So now we want the exact answer of the space outside. So we said you take the cylinder and subtract the cone. So 100 or 300 pi minus 100 pi. Pi works the same as a variable. So if it was 300x minus 100x, we subtract the coefficients and we leave x. We can do the exact same thing with pi. So 300 minus 100 is 200, and we keep the pi there. You may think, well, if a cone is 1/3 of the cylinder, you actually could do this with just finding the cylinder and then taking 2/3 of it. So 1/3 or 300 times that 2/3 would be 200, and it would be 200 pi. So it's just another way to do it. Okay, down here, number 17, the coordinates of the vertices of the parallelogram SWAN. So I'm going to label this out. So graph it. 2 negative 2, negative 2, negative 4, negative 4, 6, and 0, 8. So here is our parallelogram SWAN. I'm just doing this fast, or I would get some straight edge. And it wants us to state and label the coordinates of parallelogram SWAN, all to the double prime, the image of SWAN after the series of transformations. And if you didn't watch the hints here before, this may be your mistake as to why you had it wrong. This is a compositions of functions. It tells you to work backwards. So we're going to do the dilation first to get our primes, use our primes to do our transformation, or translation, excuse me. So we have to state them as well. So I'm going to start off with the SWAN. So 2, negative 2. You do not have to list these, but I'm just doing this so we can see where our dilation is coming from. So we're dilating it by 1/2, which means it gets bigger or smaller. It does indeed get smaller because we are taking a dilation that's less than 1. So we're multiplying it by 1/2. Half of 2 is 1. Half of negative 2 is negative 1. So you're just multiplying This one will be -1, -2. This one will be -2, 3. You can always just divide these by 2. It's the same as multiplying by 1/2. So there's our primes, and I'm going to plot those. Sorry, I have to turn it here a little bit. So also with a dilation, another way to look at this, right, is it's getting half. Everything about a dilation is about its distance from the center. So everything is half now the distance from our center of dilation, which, unless it says, is the origin. So you can see that everything has moved proportionally, which is why they're similar towards the center. We're not done yet, though, because now we're going to translate that. So we're going to translate this one going 4 to the right and 2 down. So you can count these out. 1, 2, 3, 4, down 1, 2. 1, 2, 3, 4, down 1, 2. Over 1, 2, 3, 4, down 1, 2. And down 2. So that's one way you can do this, and then you can rate them. These are double primes from there, or you can use your coordinates. So I'm just going to write them down here. Double prime. We're going to add 4. I actually, when I do this, like to do all of the x values and then all of the y when I'm doing this. So I'm going to take the 4, since I'm adding it to the x values. So 1 plus 4 is 5. -1 plus 4 is 3. -2 plus 4 is 2. And 0 plus 4 is 4. Then the y value, I'm subtracting 2. So -1 minus 2 is -3. -4, 1, and 2. And if you look, they're exactly the same. So that's actually the answer to this one up here. And then this one down here says, is it an isometry, and explain your answers. So an isometry is formed by our rigid motions. So our rigid motions are translations, reflections, and rotations. Yes, there's a translation. However, there's also a dilation, and the dilation is not a rigid motion. If you remember exactly what isometry means, it means that the corresponding figures are congruent, or that the corresponding lengths are the same, that they are also congruent. So this one is no. You have to answer it yes or no. It's not an isometry because a dilation changes the size. You could say the sides do not map onto each other. You can say they're not congruent. You can say the lengths are different, multiple things. But a point for yes or no, a point for the answer when it says explain. Okay? Number 18, find the exact value. Take this back. Let me start over. Find x in each of the following to the nearest tenth. I wrote SOHCAHTOA on here when we did the hints because it's a right triangle. We have combinations of sides and angles. We use the angle. If you got this wrong, it's possible that you used something different to label these, or you just labeled them wrong. From there, the opposite side of the triangle's opposite. The x would be then the one next to it. And of course, our hypotenuse is over here. It's across from the 90. So we have something for opposite. We have something for adjacent. So we're going to use tangent, which is opposite over adjacent. For my class, I like to write it out. I like you to write them out. I don't know if Miss Griffin makes you do that. Theta, then we plug it in. I know she uses theta, so everyone should be aware of that. Is just our variable Greek letter for angles. When we cross multiply, so we can put tan over 1. So we always put whatever you're multiplying by your trig function in front. Can't put it in our calculator yet. We divide. Now, if you do not have a trig calculator, here's how you're going to do it. I would be okay with you leaving it as 7 divided by tan of 55. Again, if you take your cell phone and you turn it on its side, it will probably give you sine, cosine, tangent. So you just have to put the rotation on your phone so that you can turn it. It will give you a calculator with more. If you look up a trig calculator on the internet, just go to Chrome and type it in that way. If you can't, leave it as 7 divided by tan of 55. Okay, you cannot figure this out other ways. The other thing is, remember, the mode of your calculator has to be in degree. So if you're using your phone one, it's possible that it is in, not in degree, but in radians. So this is how you can check it. Okay. Mine's in degrees. So to check your calculator, just put in sine of 30 and you should get 0.5. That means you're in the proper mode. If I change my mode, don't change yours yet, but if I change my mode, I'm going to get a different answer when I do sine of 30. I get negative 0.988. So when you put in sine of 30 in your calculator, if that's what you're getting, your calculator is in radians and you need to change it to degrees. You can also check this if you go onto a calculator on the internet. Just plug it in, see what you get so you can check that. That might be why you have this wrong. So I'm going to go back to degree. I can check it again with sine of 30. I'm back to 0.5, so I'm good. So x is 7 divided by tan of 55. And so this is my answer. My class, I like you to write down the 4 decimal places first. I don't know if Miss Griffin has you do that, and then to the nearest tenth. So 4.9. Okay. This one, our hypotenuse is here. We're using this angle. So if we go across, we have opposite and we have adjacent. This time we have a 9 and a 15, which is adjacent and hypotenuse. So that is cosine. So cosine of theta equals adjacent over hypotenuse. Cosine of x equals 9 over 15. So how we do that is we have to undo the cosine. So in this calculator, we're going to hit second cosine, and that brings that up. How we show the work is we take the inverse cosine and we have to flip them. That's what we have to put in. So look for that cosine of the inverse. Again, you can use your calculator. And if you left it like this, I would be okay with that. I have not talked to Miss Griffin, but I'm pretty sure she would be okay with that if you cannot put it in your calculator. I apologize, Miss Griffin, if you are not. And then 53.1301, or to the nearest tenth, 53.1. And this one is an angle, so we can label it as degrees. Okay, last one here is a proof, and I'm going to do the same thing as I did with this similar one if you were one that had to do that. My class does not do statement reasons. If you are in my class, but you learned this somewhere else, you probably used statement reasons. We just do paragraph. I'm going to do this twice. So I'm going to do it with my class, how we would do it, and then how Miss Griffin does it with statement reasons. I will do it again so that you can see it. Okay? So just fast forward to the other one if you don't do it this way. The very first thing we're going to do is we're going to start writing down our givens, and we're going to keep using our given until it's done. We want to prove that the triangles are congruent, so we need one of our 5 methods. Side, 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 angle, 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 side, or hypotenuse, leg. Okay, so that's what we're looking for to do, is 3 of those things so that we can get to the triangles. So we're going to start with the first given. IJ and FH intersect at point G. So if we take a look at these 2 lines and they intersect at G, it's telling us that for a reason. What happens when lines intersect? Well, oops, we have to write given. So we're going to do comma given. So that's where it came from. Well, that means that these angles right here are vertical angles, and vertical angles are congruent. So we can actually write that down. So angle HGJ is congruent, so HGJ, FGI, to angle FGI. And how do we know that? Well, we know that they are intersecting lines and they form the vertical angles. So vertical angles are congruent. I like to do a check mark. That means we have one of the 3. Did we use this given? Absolutely. So that one is done. Now we're going to go to our next given. So our next given is IG is congruent to JG. So we're going to look at our picture. Oops, sorry. I'm going to write down given. That's where it came from. We're going to label this. So IG and JG are congruent, which means the given is already a congruent statement. So there's 2. We don't have to go any further with that. Number 3 or 4, we have that FG is congruent to HG. So that's also a given. So we look up here. So FG and HG our given. So that's already done as well. It's congruent, so we can get rid of it. And the last one, we can just write in here because it's a given, but we actually don't need it because we've already done our problem. Because as soon as we have 1, 2, 3, we can go right to our given. So triangle Fig is congruent to triangle HJG. And our reason is, well, we look at these. We have 3 parts. We have an angle and 2 sides. So we can get all the way down to here. And it's all about, oh, it's actually an angle and 2 sides. So it has to be side, angle, side. There we go. Okay, that's it for you guys. I'm going to do this proof one more time, but I'm going to do it with statement reasons. Okay, so if we're using statement reasons for this, now when you're doing givens, they can either be listed all out first or individually. I'm going to list them out first. I'm not sure how you do it. It's up to you how you want to use those. You can also list them all in the first one. You can list them with commas between them, or you can do like 1, 2, 3, 4. It's completely up to you. And we also know that Fi and Hi are drawn. And so all of these, number 1 is given. Now, each of those givens determine and tell us something about the picture. So let's start with the first one. It says that IJ, so this segment here, and FH or HF, they intersect at G. What does that tell us? Well, if you have 2 lines that intersect, they form vertical angles, and vertical angles are congruent. Oops, so number 2 would be that angle JGH is congruent to angle IGF, and the reason is vertical angles are congruent. So we use that first one to lead us to vertical angles. I like to put a little check mark because I'm trying to find 3 things. So our 5 methods are side, 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 angle, side, angle, side, angle, 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 side, and HL. So because I already found one angle, guess what I'm not using? Side, side, side. We're not going to use that. Also, if I look at this, that would be maybe the only option for a right angle, and it's not. It doesn't say anything about that, so HL is really out. There's no right triangle there. The second given is that IG is congruent to JC. So these ones right here are already congruent. We want to label our picture, and that means we have another given already, or another set of congruent. Then we know that FG is congruent to HG. So we have another one right here. So that's another side. So guess what? We have 1,